Okay, so we dealt with vector notation and the integral form. So let's try to develop the same integral form of the mass balance again. This is slides going along with how it is done in your textbook. Again, the conservation of mass states that the rate of accumulation of mass within the control volume plus the net rate of mass leaving the control volume is equal to the rate of generation of mass in the control volume. In a number of instances, this term is 0, so basically the right hand side is 0. But there are going to be instances when you go to say kinetics and reactor design where the right hand side is not going to be 0, right, because of chemical reactions occurring. So again, for any problem, please write down the statement of the mass balance, and your goal is to evaluate it term by term. So your goal is to evaluate what is the rate of accumulation of mass, what is the net rate at which mass leaves, and what is the rate of generation of mass. This is your starting point, so please memorize the statement of your mass balance. You got to write it down and evaluate it term by term. So let's go ahead and do that. So again, this is just an arbitrary control volume in space. The surface bounds the control volume, right? And the mass can cut across the surface and can come in and can go out. And what is shown here is mass A, the fluid going out. So how do you do the mass balance? Is basically you take a small area dA, you calculate the mass flow rate through the small area dA, and then you integrate it over the full surface area. You're going to get the net rate at which mass leaves, right? So calculus. Okay, and this slide you did see in the vector notation video before. When the velocity comes in at an angle v to the surface area, right, and the angle between the velocity and the unit normal is theta. How do you calculate the mass flow rate? You take the dot product of v with n. Rho v dA cos theta gives you the mass flow rate through elemental area dA. And when you integrate this over the full surface area, you get the total mass flow rate, right? Simple. And again, which is what is shown here, this is the mass flow rate through a small elemental area dA. Integrated over the full surface area, you get the total mass flow rate. Okay, and again, there is another very important thing that the v dot n takes care of, right? Because at exit, v dot n is greater than 0, so cos theta is always going to be greater than 0. And if the angle between v and n is 0, then cos 0 is 1. So while at the entrance, if both n and v are in the opposite direction, which occurs at inlet, then the angle between them is 180, and cos of 180 is going to be minus 1, so cos theta is going to be less than 0, right? So taking the dot product of v with n also serves another important purpose. It helps identify whether the fluid is coming in or going out of the control volume, right? So the term rho v dot n dA integrated over the full control surface gives you the net rate at which mass leaves. What is the rate of accumulation of mass? Is how the mass inside the control volume is changing with time, right? So rho dV integrated over the full control volume, that's why you have 3 integrals, because volume has 3 dimensions, right? Gives you the total mass inside the control volume, and how that is changing with time gives you accumulation. Simple, nothing complicated. And obviously, when you go to say kinetics and reactor design, or even in MEB2, you're going to have a reaction rate, which is say kg per meter cube second, the rate at which mass is being produced or consumed. Now you integrate that over the full control volume. This gives you the rate of generation of mass, right? So for simplicity, the book assumes the rate is 0. So, and obviously, but please keep in mind, this is what you do in kinetics and reactor design, where you got to design reactors where chemical reactions are taking place. So, so you got to do a mass balance with this term as non-zero. So again, overall mass balance, very simple. Net rate at which mass leaves plus rate of accumulation of mass is 0. And as you can see, by writing it in simple integral forms, it saves a lot of time and effort. And this is the starting point for a number of problems that we will be solving. And from now on, you're going to see this quite a lot, right, as we go along in the chemical engineering curriculum. Okay, closure on page 37. I think it is page 37. I don't know which edition this is, but this is the end of the mass balance chapter. So in this chapter, we have considered the first fundamental laws of fluid flow, conservation of mass, and this is a very general form, can be used for a lot of problems. And our goal is to develop such integral expressions for energy and momentum. You're going to see it's going to be very simple. So please, this is always the starting point, right, for a particular problem. And I have seen in previous years, again, there will be strong temptation simply to write down an equation without considering each term in detail. So please overcome such temptations. This approach may seem tedious at the outset, but will always ensure a complete analysis of a problem and circumvent any errors which may otherwise result from too hasty consideration. So please start off, state your mass balance, look at it term by term, and evaluate it. This will really serve you in good stead as we go along, and we will work on more of the problems, right, as we go along in this course.